omega t with certain omega or physical frequency f, which is 5 sine 2 pi f, where f is the physical frequency. So it is going to look like this. So where the peak amplitude is 5 here and negative peak is negative 5. Okay? So this is the voltage Vs as a function of time. X-axis is time. Now, what you do, I ask you to show this input on the scope. Let's say this is your scope. You have channel 1, this is channel 2. Each channel has, let's say, a cable that has 2 outputs. This is positive and the other one is negative. So this is your negative. This is basically arc ground. This is arc ground. Okay? So when you show the voltage signal in channel 1, what you do, you put this channel 1, you connect it right here, and your negative, you put it right here. That way you see the input signal on channel 1. Now, if I ask you to show the voltage across R2, for example, I want you to show me the voltage across R2, which is identical with V2. Okay? So, most of the time, the mistake that you guys do, if you show this on the scope, most of the time the mistake that you do, what you do, so you put one channel right here, the other channel 2. Channel 2 has 2 wires. So one is positive, the other one is negative. What you guys do, you put this one here, and we put this terminal right here. This is incorrect. So this connector here, this is arc ground, which means that this is 0 volt. This is arc ground. So you don't connect this negative right here. So in that case, you don't get the actual voltage. This voltage the way you should be measuring is the following. Consider this as node A. So the voltage at this node is V sub A. This voltage means voltage of this point with respect to ground. Voltage of this point with respect to ground. And voltage of this node, let's call this node B, and voltage of this node is VB. And the voltage of this point is with respect to ground. Then V2 is going to be V sub A minus V sub A. You guys understood? It is the differential voltage across any of the voltage of this point is also differential voltage. Only thing is that this is zero. You subtract this this voltage, node voltage minus this 0 is going to be this voltage. Okay? But if you want to take voltage across any other resistor or any other component between two terminals, it's basically a differential voltage. You always keep that in mind. So for that, what you do, you take a node voltage using channel 2. So what you do, you connect channel 2 positive terminal right here, and channel 2 negative terminal, you connect it right here. And to get the voltage of this point, what you do, you have another channel, let's call it channel 3. Okay? So channel 3, the coaxial cable is coming right here. And then you have this positive terminal and you have this negative terminal. And this negative terminal should be this grounded, and this positive terminal you take it and connect it right here. So now you have this V sub A and you have V sub B. Now using scope, you have to use math channel. You have to use math channel. You have to use math channel. Math channel to subtract channel 2 minus channel 2 to get the voltage across R2. Did you guys understand? Clear? Crystal clear? So you have to use math channel. So if you don't know how to use math channel, we have dealt with that. Okay? So just ask a question, TAs, my TAs, and we will be glad to help. Using PSPICE, what can PSPICE? So let's open this overlap rectifier. This is part 4 of your laboratory experiment. Okay. So I have here the voltage. I want to show the input voltage, and I want to see the voltage between this resistor R1. So what I did, I put 2 probes right here. I put two probes right here. And this is basically differential probe. So what you could do, you will see, so it has this differential probe. So you can actually put 2 terminals right here. So what PSPICE does, it actually gives you the difference between this node, the voltage of this node, and voltage of this node. Okay? If you don't use differential probe, what you could do, you can use this single probe voltage, one channel you put it right here, the other channel you put it right here. After that, you will have to use trays. You will have to use you will have to add another trace and supply one voltage from the other. So using, let me show you, I'm just running it. Here, I use differential probe, that's why I can see the output better. So what you could do, if you use just single probe, then I'm just going to let's close this. If you use single probe, right here, this is voltage across R1 mode 1, and you have another voltage right here. Okay. So now if you run PSpice, so now it is showing the voltage of one terminal of the resistor in green, the other terminal of the resistor is in red. What you will have to do, you will have to add another trace. You can say right click and add trace. And then you just have to write the formula. It is V R1 voltage across R1, it's pin number node 1 minus V R1 and it is node 2. You see that? So if you click OK, do you see? You can change the color. This property. Use this color. Let's use this color. And make full. You see that it's the same thing. Clear? Yes.
You do this only using voltage level markers, right?
Yes. Yes. So it is the same thing. Either you use single probe voltage level, voltage marker, or you can use the differential. So, but you will have to know what these two options are doing. Okay? You guys understood? Clear? Crystal clear? Okay. All right. There are some other circuit simulators as well in MATLAB Simulink. I teach this in mechatronics. It's called SimScape. SimScape. Using SimScape, you can draw exactly the same circuit. Only thing is that in SimScape, you need to add another solver. Here, it actually gives solver comes with solver comes right here. So PSpice, when you create new simulation profile, you actually give the solver right here. Okay, that is the only difference. So in many circuit simulator, main principle of simulating a circuit is pretty much the same. Only thing is the different options you see in different simulation software. Alright, so I'm going to close this. Now I'm going to start today's lecture. Just right before coming to the lecture, I uploaded the latest version of my slide, which is module 3. And module 3, we started module 3 in our last lecture. And this module 3 consists of chapter 3 and chapter 4 of the textbook. So I will go directly to the page where we stop. Okay. So in our last class, we considered this diode as a switching device, and the thing is, we consider this diode as an ideal diode. Ideal diode. Ideal diode means, okay, again, I'm going to use the same concept. If we have a diode, what is the name of this terminal? This terminal? What is the name of this terminal? Anode. And this terminal is the cathode terminal. In LED, anode terminal is a bit longer, and cathode terminal is short. Short leg is the cathode, and long leg is the anode. Now we are going to say the voltage of this terminal, I'm going to denote it with V sub A, and voltage of this terminal, I'm going to denote it with V sub K. So K for cathode, okay? And we do not use C because DC, it means that the voltage across capacitor. You know, in electrical engineering, we use C for capacitance. So that's why I use V sub K to denote the voltage of the cathode terminal. V sub A is the voltage of anode terminal. Again, when I say voltage of anode terminal, V sub A means that you have a common ground which voltage is 0. So voltage of this point with respect to ground. And V sub K, this voltage means voltage of this point with respect to 0. So V sub D, therefore V sub D is going to be V sub A minus V sub K. Very important. So V sub D, the voltage between these two terminals, voltage between anode and cathode, we call it V sub D. So anode voltage minus cathode voltage is going to be the voltage across the diode D. Now, this VD is this voltage minus this voltage. When the anode voltage is greater than cathode voltage V sub K, that means this diode, you can just simply replace this diode with a piece of wire. When V sub A is greater than V sub K, you can just replace this diode as a piece of wire. So therefore, you see whatever voltage you have, you see that voltage across these two terminals. Now if you have V sub A minus V sub K, which means that the anode voltage is less than the cathode voltage, in that case, you can think of this as an open circuit, no connection between these two terminals. We are considering ideal diode. Okay. So if that is the case, then you see it's simply half-wave rectifier, and you see the positive cycle on it. And you saw some of you showed it out. So this is what we had in our last class. Now let's go through one example that we did not go through. This example, I adapted this example from example 4.1 of the textbook. So in the textbook, for example, author said that 24 volt sinusoidal signal. I actually gave actual expression for the input. So V sub S T is 24 sine omega t with some frequency. So here, this input is the input that is given right here. Okay. So this is V sub S, and the unit is volt. Okay. And x-axis is this time. Now let me go to another vector. Okay. said that, okay, we have input voltage V sub ST, which is A sine 2 pi f t, where we view the sinusoidal signal as such, where the amplitude is A and negative amplitude, the minimum amplitude is negative. So this is your positive, and this is your V sub S T, and the unit is volt. Okay, this is the unit. And x-axis is time. Now we can actually draw this x-axis instead of time. We can have it in angle. So we can actually write it in terms of theta. So V sub S angle theta is A sine. Okay, so this is A sine omega t. What is omega? Okay. Omega is angular frequency, right?
Pi f, yeah.
Yeah, angular frequency, 2 pi f, it's an angular frequency in radians per second. Okay, angular frequency or angular rate. Okay, angular velocity, radians per second, angular velocity. Now, when you multiply this angular velocity with time, what do you get? You get the angle, right? Angular velocity multiplied by time, you get the angle. Like that angle is basically A sine theta. Okay, so omega t is basically theta. Now we can actually draw this, where the y-axis is going to be V sub S at an angle theta. Again, the unit is going to be volt, and x-axis is going to be theta. Theta you can put in degrees or in radians. So in that case, theta right here is going to be 0. Theta here is going to be 90 degree. In other words, pi over 2. Theta right here is going to be 180 degree. In other words, it's pi. Theta right here, it is going to be 270 degree. In other words, it's going to be what?
It would be 3 pi over
3 pi over 2, right? And angle right here is 360 degree, which is going to be 2 pi. Okay? So that angle, we can write this signal as a function of angle as well. So just keep this in mind. We have two different x-axis. The x-axis here time, here it is angle. And this angle is nothing but omega t, angular rate times t. So we are going to use this concept in the following. Here, V sub S t 24 sine omega t, we have this signal where x-axis is theta. I put radian here, so in terms of radian it is 0, and this is pi over 2 radian, this is pi radian, this is 3 pi over 2, and this is going to be simply 2 pi, which is 24 sine theta. R here is 100 ohm, and ID is the current flowing through this diode. For charging a battery, so this here you have, this is our battery, we are charging this battery. So it's 12 volt battery that we are charging using this AC signal. Okay? Using this AC signal, we are charging this 12 volt battery. Now, question here. Okay, guys, this plot, entire plot, I put it here, this is part of the solution. Solution, and I'm going to mention one at a time. So I did talk about the input signal that is given. So this is our input signal. This is our input signal that is given, and we are given R equals 100 ohm, and the battery voltage, the battery is the 12-volt battery that we are trying to charge. That's all we are doing. So we want to find the conduction angle. We want to find the conduction angle. So in other words, conduction angle. Here angle is 0, 90 degree, 180, 270, 360, and so on. So we want to find the conduction angle. Conduction angle delta theta, fraction of each cycle of ds. So this is one cycle. So it is going to be fraction of one cycle during which diode conducts. Okay. And the second question, find the peak amplitude of the diode current IG that I drew already. Okay, and I'm going to show you how we find the diode current IG and the maximum reverse bias voltage that appears across the diode. Okay. So we'll be using KVL. We cannot, as an electrical engineer, we simply cannot forget KVL. Okay. So we'll be using KVL, and we'll be using some mathematical functions, and then we'll come up with different solution. So we are given ds t equals 24 sine omega t. We don't know what is the frequency, which is basically ds in terms of theta. It is 24 sine theta. Okay. R equals 100 ohm. The way out the solution is a little bit different than what author provided. So each person can have different solution, but the end result is the same. And the battery voltage we have, the battery voltage, the battery that we want to charge, the maximum charge is 12 volts DC. And we are going to consider this as an ideal current. Okay, now come back to this circuit. Try to understand how this circuit works. You have to know the working principle. So, because we have this nonlinear device diode, okay? Because we have this nonlinear device diode, this diode only conducts. This diode is going to be a short circuit. The diode is going to be a piece of wire, short circuit. When only the case when the anode voltage, the anode terminal, which is this voltage, V sub A, and this voltage I'm going to call it V sub K. So only when is V sub A greater than V sub A greater than V sub K. That is the only time this diode is going to conduct. It means that you can just think of this as a piece of wire. Okay? You can just think of this as a piece of wire. Now, when this will happen, look, we have this voltage. Voltage starts from 0, okay? And this voltage goes up to 24, right? Right? This voltage goes up to 24. Peak voltage is 24. So this voltage is, goes to 24 volt. So therefore, if battery has 0 voltage, no charge, in that case, this voltage is going to be more than this voltage, right? So it is going to conduct. So it is going to conduct until it charges. But in the question, it is given that the battery is fully charged. In the question, it is given that the battery is fully charged, which means 12 volt. It is given here. So VB, this battery has a voltage of 12 volt. So this diode is not going to be on until this anode voltage is 12. Clear? So when anode voltage is 12 volt, which means this voltage is going to be, it's going to be this here. When you see that this is 12 volt, then you see that little over 12 volt, then you see that this voltage is going to be greater than this voltage, and you can see that this is.
Can you substitute 12 in for VK?
Yeah, VK is going to, VK here is 12 volt. Okay, because this node voltage is 12 volt already. Good point. So when this voltage is little over 12 volt, nano voltage, then it is going to come. Now you see that input voltage is more than 12 volt, which means that diode is on. It is going right here until input voltage is less than 12 volt, right? So from this point to this point, diode is going to conduct. Okay, diode is going to be simple. You can think of this as a piece of wire. It is going to conduct from this point to this point. So therefore, the angle corresponding to this point, let's call this theta 1, and angle that corresponds to this point, let's call this theta. So we can actually say, for the first point, that find the conduction angle. So we can actually say that diode conducts when 24 sine theta is greater than VB. You can say that VA greater than VK, and which means that VA has to be 24 sine theta greater than VB. In other words, VB is going to be 12 volt. So in other words, sine theta has to be greater than 12 over 24, which is now sine what angle, sine of what angle gives half? Sine what angle gives half? Sine 30 degree. Sine 30 degree. Okay? Sine 30 degree, right? Sine 30 degree is half. And what angle gives another angle?
60 also.
Sine 60.
Sorry, not 60. That's fine.
It is going to be, so the two theta values, sine 5 over 6 is going to be half, and sine 5 pi over 6, 150 is going to be half. So between these two angles, you can say like 2 pi over 6 is going to be more than. Sine 2 pi over 6 is going to be more than half. So between these two angles, sine of these two angles is going to be more than half. So therefore, theta 1 is going to be half. Theta 1 is going to be pi over 6, and theta 2 is going to be 5 pi over 6. So the conduction angle conduction angle delta theta is going to be theta 2 minus theta 1 is going to be 5 pi over 6 minus pi over 6. It is going to be how much, guys? Yeah, 2 pi over 3. So how much is it in terms of degrees?
That would be only
120. So conduction angle is going to be 120. So this is one answer. So delta theta is going to be 120. Yes.
Why do we not include the plus 2 pi n in our answer?
Yes, you can say 2 pi n, okay? But you can 2 pi n means you have multiple cycles of input, right?
Yeah.
So always the conduction angle is going to be always, the difference is going to be always, always one way. It doesn't matter what cycle you take, difference is going to be always 120. Okay, make sense? Okay, so which means that here I actually drew these vertical bars I actually drew, so therefore this conduction angle delta theta in other words 3 pi. Okay, this is the conduction angle. Now it is time to find the current. Find the peak amplitude of the diode current I. Don't you think that when the diode is on, which means that it is going to be a piece of wire, so current is going to flow. So in that case, I have the diode current axis is ID right here, ID ampere. Okay? So diode current ID is going to be, this current is going to be whatever this voltage we have, it's a piece of wire, whatever voltage we have, minus this voltage divided by R. So you can think of this as a piece of wire. So this current is going to be, ID is going to be V sub S angle theta minus VB over R. This is the current expression. So diode current ID is going to be V sub S theta minus V sub B over R, and that is the general expression. So it is going to be 24 sin theta minus V sub B minus 12 over R is 100. Okay, and the maximum diode current. Now, if you look at the y-axis, ID, okay, the ID is going to be, look, there will be no current until this point. After that, diode current will increase because the voltage is increasing, right? Diode current will increase. So until this point, there will be no current. So no current is zero until this point. 5 over 3, that's 6. So after that, diode current is increasing up to this point. After that, your anode voltage is less than the cathode voltage, therefore the diode current is going to be reverse bias. Diode current is going to be zero. Did you guys understand? Why current plot is like that? For current, I have y-axis this way, so it has different scale. So in that case, so the diode current is going to be, see, I say it here, 24 sine theta minus 12 over 100 and 0, because diode current is not going to be negative. So the maximum diode current is,
Does it occur when theta is 90 and sine is equal to 1?
yes, exactly. That's what I'm going to do. So maximum diode current, the peak diode current, IB max is going to be 24 sine theta minus 12 over 100, and when this sine theta is going to be maximum, this guy is going to be maximum when this sine theta is going to be 1. Okay? So when theta is 90. So which is going to be 24 minus 12 over 100. It is going to be, how much is it? 12 over 100. It is going to be 0.12 ampere. Okay? That is the maximum diode current. That is the maximum diode current. So if you look at this plot, I use computers to draw this plot. Okay, so the maximum diode current is going to be here. The maximum is going to be 0.12 ampere. Other than that, it is going to follow a sine wave. So here, when theta is greater than 30 degrees, it is going to follow this theta equation, 20%. But the maximum is going to be 0.12 ampere. So this is the peak amplitude of the diode current, and we want to see the maximum. We want to see the maximum reverse bias voltage. So the maximum reverse bias voltage so we have anode voltage here. Anode voltage here V sub A, and here cathode voltage is V sub K. So reverse bias voltage VR, reverse bias voltage, I'm going to get into the VR. VR is going to be Vk minus V sub K. So this is the maximum reverse bias voltage. So the reverse bias voltage you can apply diode. Voltage VR is Vk minus V sub K, cathode voltage minus anode voltage. Now the cathode voltage is what? 12, right? And the anode voltage is 24. Sine theta. Maximum. Maximum here happens maximum here happens. Okay, when here is going to be maximum, right? 12 minus 24 sin theta. And 24 sin theta is going to, when this guy is minimum, right? When this guy is minimum when? No.
No, I think it's referred to by the reduction rate.
Yeah, no, it's Vs, when Vs is minimum. So Vs is going this way, when it is the minimum. Negative 24, right? Okay, this is sine wave. 24 sine wave, which means that the peak amplitude is 24 and the minimum peak is negative 24, right? Okay, so this Vs is going to be minimum when it reaches the negative peak. Yes,
Why are we considering reduction angle in this case?
here I'm not considering conventional.
Yeah, why?
Oh, because it's not in conduction, because I said that this voltage is more than this voltage, reverse bias voltage. Okay, so diode is not in conduction. Okay, so in that case, diode you can think of this as an open circuit. And open circuit, and I want to know the maximum reverse bias voltage, which means the difference between cathode voltage and anode voltage. So VA minus VN, so that is the reverse, that is the definition of voltage. So diode is off. The maximum reverse bias voltage here happens when Vs equals 24 sin theta equals negative 24. So VR, you can say max is going to be 12 minus 24, which is 36. So VR max is going to be 36. That's the final answer. You guys understood? So the reverse bias voltage is the difference between the cathode voltage and the anode voltage. And the forward bias voltage is the difference between the anode voltage and cathode voltage. Okay. So after that, we are going to move on to a slightly different version of the circuit. Is it okay? Slightly different version of the circuit. It's called limiting or protection circuit. In case the input voltage goes beyond certain limit, we don't want to damage the circuit. Okay? Circuit behind underlying circuit that we are working with, we don't want to damage that circuit. So we want to limit the voltage. So diode can actually do that. So this is a simple positive limiter circuit. So we have limiter voltage is going to be limited by the DC voltage right here. Okay? Again, we are considering ideal diode. Here, we are considering ideal diode. And we are coming to the construction. There we will not consider the ideal anymore. Okay. Ideal diode. Now, look. Again, this is my V sub A, and this is my V sub K, cathode voltage. So the diode will conduct when this voltage is greater than this voltage. And this voltage, total voltage here is going to be V sub I. So diode conducts when V sub I, this voltage, which is going to be V sub I, greater than this cathode voltage, which is V sub V positive. Okay? And we take the output across these two terminals. So the output voltage V sub O, V naught, is clamped to approximately V plus. So output voltage is going to be maximum is going to be V plus. So when diode conducts, when diode conducts, you can just think of this diode as a piece of wire, when Vi greater than V plus. Okay, you are taking this as a piece of wire. Now you can think of this as a voltage source. What is the voltage between these two terminals? If you take a voltmeter, what voltage you will get? This voltage is going to be simply V plus. So it is going to be this voltage, and then when diode is off, which means V sub A less than V sub A. So which means this voltage is less than this voltage. In that case, what is the voltage between these two terminals? In that case, you have these two terminals simply open. So if these two terminals are simply open, no current will flow. Whatever voltage you see between those two terminals, this is going to happen. That's why you see the entire beginning. The entire beginning cycle is going to be when diode is on. So when diode is on, no current will flow. You see whatever is on this source. So that's why we are here simply limiting the positive cycle, not the negative cycle. So this is simply one simple limiting cycle. So I have little explanation here of it. And this example is also this example that scribe. Example 4.4, please. Yeah.
So if you flip the diode around, would it change it to a negative limiter circuit?
Now you have to look at the operating principle. If you flip the diode.
Yeah.
Okay. So in that case, depending on the you will have to flip this source as well. You will have to flip this source as well. That way you can see that it is going to be positive. Yes. Okay. All right. Now little applications like in case input over voltage protection, this application input over voltage protection for sensitive circuit and voltage clamping for signal processing. So this sort of basic ideas will come handy when you design complex circuit where you have very sensitive circuit where you don't want to have over voltage over certain voltage that you want. Now let's talk a little bit about the construction of diode. So far, we consider diode as a simple piece of wire when anode voltage is greater than cathode voltage. So we consider this as a piece of wire. Okay? When anode voltage is less than cathode voltage, then we consider this as an open circuit. Okay? Practically, it is not the case. Let's look at the construction of diode. Diode is constructed with semiconductor cathode. So diode is constructed with semiconductor materials. Now, semiconductor is pure pure semiconductor crystal. So this is pure. Semiconductor crystal where atoms are arranged in regular layers, where we have 4 electrons, and these 4 electrons are basically holding each silicon atom. You can think of this atom. Each silicon atom shares 4 electrons with neighbors, forming covalent bonds. So each silicon atom is going to be in covalent bonding through 4 arms like that. Okay? So the structure, the pure silicon semiconductor structure will be like this. Okay? So these are silicon atoms, and then we have 4 electrons that are basically holding other 4 atoms. Okay? So at room temperature, thermal energy frees some electrons, but at absolute zero temperature, no free electrons. So if there are no free electrons, no electricity will be conducted. So we want to free some electrons. We want to free some positive charge. We want to free some negative charge. If you can free some positive charge and negative charge, then, only then, you can think of the existence of matter. Okay? How we do that is a point. Okay. In the exam, guys, I'm not going to ask you, give me the terminologies of what is doping, what is giving, what is hope, what is recombination. It is just for you to understand. You just have to understand how it works. Exam is going to be mostly problem-based. Okay, so I'm just going to make you understand, and it is available. I'm not going to read my slide. I made it very concise and nice, available to you. So I'm just going to give the high-level description. Doping process. Okay. Here you add some impurity to the pure semiconductor matter. You intentionally put some impurity, some atoms. So we call it dopants. Doping process, the process of intentionally adding small amounts of impurity to impurity atoms to a pure semiconductor to alter electric properties in this conductivity. So you need some dopants for the semiconductor material to conduct current. So once you have some doping, an electron in the conduction band of the semiconductor process, it's going to free some electrons, and this electron will be moving under the influence of electric field, contributing to electric current, and that's where electric current comes into existence. In semiconductor. So in semiconductor materials, you have to have doping process, or you have to, in other words, you have to add some dopants or impurity for electricity to conduct, to exist some electricity. Without dopant, without impurity, you simply cannot have electricity in pure silicon materials. And in case hole, what is hole? Hole, in case you add some dopants, but in that case, it's going to be positively charged particle. Once you add some dopants, but that is going to be positively charged particle. And positively charged particle also contributes to the electric current. Positively charged particle and negatively charged particle, both of them contribute to electric current. And recombination process, once you have some doping process, sometimes it may recombine. Recombination process will make the electrons move on to holes to lose energy. So that's what the process in which free electrons loses energy fall back into holes in their valence bond, effectively eliminating both the electron and hole as charged chemical. So it's going to be neutral. Okay, so that's the recombination process.
So recombination happens is the diode useless?
Yeah, so in that case, if recombination happens, diode is continuous. No characteristic. Okay? So now let's look at the construction process. Now we are going to add some, we are going to go through some doping process. We are going to add some liquid. Okay? Okay, once you add phosphorus, I also do chemistry. All engineers, they have to take chemistry. I do chemistry. But yeah, phosphorus, the symbol is P, and I don't know it's in, what's that table called, guys?
Yeah.
Periodic table. Yeah, periodic table. Right? It was, I memorize it. I'm not sure. If you guys found some ways to memorize that periodic table. What we do was just practice. I practice a lot. But still, I don't know what's the, what place this phosphorus in the periodic table. But anyway, here we are going to see the application. You add phosphorus means that you are adding an electron to that silicon battery. As simple as that. You add phosphorus means you are adding an extra electron. That electron can be. You add boron B. The symbol is B. You add boron means you add a hole, positively charged chemical. Okay? So that's the impurity. So we add phosphorus to create a free electron. If you don't add doping, so it's going to all the electrons is going to hold in other atoms. There will be no charge carrier, no electricity. But once you add phosphorus, you are adding electrons. So you are adding extra electron here. Extra electron. Once you add boron, you are adding a hole. Hole means positively charged carrier, electron is negatively charged carrier. Now here I have a little explanation. N-type silicon, if your doping process, if your dopant is phosphorus, which means that you have doping with phosphorus, which means that you will have 5 electrons instead of 4, you will have 5 electrons, it adds 1 free electron. So this becomes an N-type semiconductor, N-type silicon battery. Once you complete the doping process with phosphorus, it becomes N-type silicon or N-type semiconductor material. Once you complete the doping process with, if you pursue doping process with boron, then it creates a hole. So you have 3 valence electrons and it creates a hole. So that becomes a p-type semiconductor battery. So you have n-type semiconductor material. Once you pursue doping process with phosphorus, you have n-type semiconductor material. Once you pursue doping process with boron, you have p-type semiconductor material or p-type silicon. And the other two terminologies, charge carrier. So we said majority charge carrier, minority charge carrier. Charge carrier, majority charge carrier, you will have, in majority charge carrier, you will have more free electrons in N-type material, and you have in majority charge carrier, you will have more holes in p-type material. You will have more electrons, free electrons in N-type material. So this becomes majority carrier, and if you have more holes in p-type material, that becomes a majority charge carrier. Holes. In that case, majority charge carrier would be holes, and in case you have more free electrons in N-type material, majority charge carrier is going to be free electrons. Minority charge carrier, you will have more holes in N-type material. That's the opposite. You will have more holes in N-type material, and you have more. Holes in. You have holes in N-type material. Yeah. You have holes in N-type material, and you have electrons in p-type material. So that becomes minority carrier. Minority carrier, holes in N-type and electrons in p-type. Now, how current flows? Again, we are coming close to the construction of current. So you see that we have anode and we have cathode. So I still didn't say formally, but I tried to draw from the textbook. It's not complete. You can see it's going to be very similar to the textbook. So I just didn't want to take a screenshot that I wanted to draw, so that's why I wrote here. Check. But you can see similar picture in the textbook. So now current flow in semiconductor. Current flow in semiconductor, we have two types of current flow in semiconductor. One is called drift current. Drift current is caused by electric field. Electrons move in opposite to electric field. Okay. Holes move along electric field. So this is the current, drift current direction. This is basically the diode current, IT. Okay. This is basically the diode current, IT. Okay. So it's caused by the electric field. Electrons move in opposite direction. So electrons will be moving in this direction, and holes will be moving along the electric field. And diffusion current is basically the concentration of charge carriers. So charge carriers concentration. Charge carriers move from high concentration to low concentration. So that becomes a diffusion current. So total current is going to be sum of drift current and drift plus diffusion component. So the direction of pole current is the direction of electricity, and direction of electric current is going to be opposite to electric field. Now we are going to form the p-type material, p-type semiconductor and n-type semiconductor together. So we are going to join them together. Okay? So that is basically the diode construction. So we have the p-type material and we have n-type semiconductor material. P-type semiconductor material, n-type semiconductor material, we are going to join them. Okay? That becomes the diode. Okay? So what we have here is we have p-type semiconductor. We see that p-type semiconductor, we have what? So we have silicon material when it becomes p-type. What we do? We add boron, right? Boron as an impurity, that becomes a p-type. Okay? And we have n-type semiconductor. So we take silicon material, pure silicon, and then we add phosphorus to become an n-type. Okay? So we have n-type silicon material, we have p-type semiconductor material, we are going to join them together. And then we add metal conduct for biasing, so that we apply voltage for biasing. We have metal conduct, and then when we join together, it becomes there becomes a barrier. Okay, barrier. There you will see. There you will see it is 1050. So 1050. I am going to stop right here. We are going to continue from this place now next place. You guys are okay? This one there? Thank you. I will see you.